Well, guys, there's one more equation I want to look at, okay? And here it is, number 11, okay? Um, Sine of x minus radical 3 cosine of x equals 1, okay? There's a couple things to take note of with this, and there are things that we need to amend, obviously, as you can see with the work ahead, uh, that we can't dismiss, okay? We've got the equation expressed in terms of two different functions. Until we get them represented in terms of a single function, we're not going to be able to get anywhere. So that's where we stand with this problem. Now, typically those equations involving sines and cosines, as is the case here, uh, would require us to implement the Pythagorean identity, sine squared plus cosine squared equaling 1, to move us in the right direction. Uh, that is what we're going to take advantage of here, but we're not even ready to implement that because in order to do that, we need to have the expressions uh, in the form of sine squared and cosine squared, which obviously we can see we do not have at this stage. So to facilitate that, it would we would presume to square both sides. And prior to squaring both sides, it's to our benefit to move one of these function terms, either cosine or sine, to a side by itself. So that's how we're going to proceed. As you can see, I'm moving this cosine expression, radical 3 cosine, to the right side in the first step. Then I'm going to square both sides, okay? And of course, squaring both sides in this line implies the sine being squared, just as you can see, sine squared. But this expression as a binomial, 1 plus radical 3 to quantity squared. I don't know where that radical sign's going, but there it is. Okay, and so that's like squaring a binomial, a plus b to quantity squared, which, as you should recall, is of the form of a squared plus 2ab plus b squared. So that's the little algebra getting from step 1 to 2. All right. Then I'm going to collect this. I'm going to shoot this cosine squared to the other side. Okay. And now the question is, why did I decide to go with renaming the sine squared? Well, only because I have two of my three trig expressions are with cosine. I might as well put that third one in terms of cosine too. So the Pythagorean identity offshoot of sine squared plus cosine squared equals 1 is what we take advantage of here with renaming the sine squared as 1 minus cosine squared. Okay. Sorry for this all this formatting issues that are going on. But okay, so we're back here. Now, doing that then allows us to condense these two cosine squared terms, as shown here, just remove the parentheses, and then down here into the negative 4 cosine squared x minus 2 cosine minus 2 radical 3 cosine x. The ones on the beginning and ending were fortunately canceled out. Okay, so that seemed like a lot to get down there, and of course it seems like we still have a lot to go, but such is life. So here we go. We're going to factor this um, by removing the common factor. The greatest common factor is negative 2 cosine x, uh, which will give us the expression cosine x, radical 3 cosine x plus 1. I'm sorry about this, all this formatting stuff going on. Okay, so each of those factors is now set equal to 0. All right, each of those factors is now set equal to 0. And of course, this collapses to cosine x equaling 0, which we know is the intercepts of the cosine, which happen to pi over 2 and 3 pi over 2, and then again with the regular period alterations of plus 2 pi k on both of them. And then over here, we have the cosine of x equaling negative 1 over radical 3, which is alternately written as radical 3 over 3 negative. cosine being negative in the second and third quadrants with reference angles of pi over 6 result in the 5 pi over 6 and 7 pi over 6 solutions in each wavelength, and of course plus the 2 pi k for all subsequent wavelengths. Okay, now so let us go to the Desmos, take a look at our graph, okay, of this expression, okay, which is uh, apparently offering us the four solutions per cycle. So let's go to Mr. Desmos here, okay? So here is our expression. This was the original expression down here. We'll look at that momentarily, okay? But our expression here of -4 cosine squared minus 2 root 3 cosine is graphed as shown here. Now, don't worry about how you would ever get that graph. And, I'm not concerned that you can get that graph, at least not at this stage of the game, and maybe not even within this course. But the objective here is to use the graph to match the solutions, okay? But then we're going to show you a little anomaly that develops here with that. Our solutions, as you recall, we got the pi over 2, we've got the 5 pi over 6, we got the 7 pi over 6, and we got the 3 pi over 2. So that validates our solutions there, okay, from the analytical approach we took to solving it, the original equation. But now, okay, now, oddly enough, okay, I'm going to call on graphing the original expression. There's our original expression graphed in blue. Does not even remotely resemble the expression that we previously graphed. Okay, and of course you're going to wonder why. And the blue expression, the graph expressed in blue, has only two solutions per cycle. Now, why is that? And of course, we do see that those two are in a line with our original, with our calculated values. Why is that? What is going on here? Okay, let's go back. Let's go back and decipher this. Okay, here's your original expression. All right, sine x minus root 3 cosine x equals 1, and that graph was not coincident with this graph that we found down here. And the solutions were not coincident, as we could see from the Desmos variation. Why? Ask yourself why. Ask yourself why, please. What did we do? We had to square. We had to square both sides. What did we caution you of very early in solving equations, in solving any kind of equations? That was if you alter the original equation, okay, by doing things like squaring, as we just did, all right, you introduce the likelihood of extraneous solutions. And that's what we got. Okay, we got extraneous solutions. We got the solutions to, okay, the altered equation, okay, half of which are acceptable for the original equation. That was made obvious by the graph. Okay, here's our um, original equation in blue, offering us 2 intercepts per cycle. Okay, here's our solutions to the altered equation resulting from the squaring of both sides. Okay, only which two of which per cycle line up. So what two do we take? We got to go back to the original equation. We got to accept the only two solutions per cycle, okay, um, that will fit back in the original equation, and we have to discount. Let's see, which ones we have to discount? 5 pi over 6. 5 pi over 6 is, is going to be discounted, and 3 pi over 2. Now, what I've done back here was I validated that they were not viable solutions by plugging those values back in to my original expression up there, sine minus radical 3 cosine. I plugged in those values, okay? Evaluate that original expression for 3 pi over 2. Done here, we are not balanced, okay? Sine of 3 pi over 2 is -1. Cosine of 3 pi over 2 is 0 times whatever is still 0, resulting in a -1 equaling 1. Obviously, a no solution, okay? Likewise, the 5 pi over 6 was also placed back into the original expression. The sine 5 pi over 6 resulting in 1/2, minus root 3, the cosine of 5 pi over 6 resulting in root 3 over 2. The product of that with root 3, of course, is 3 over 2, and 1/2 minus 1.5 gives you -1/2, not the alleged 1 that it would have if it were a balanced equation. So, what do we take away from this? Okay, in this equation, as in any other equation, trigonometric, logarithmic, exponential, polynomial, whatever, altering the original equation, okay, for purposes of making a better defined solvable equation, okay, by doing such things as squaring both sides, introduces the likelihood of extraneous solutions. Okay, don't forget that. I mean, I know it's a rather detailed problem. Okay, but it is a valuable concept that you've got to be you have to understand and be understanding of when you're solving these equations or any other equations. There you go. Okay, hope that was valuable for you.